In today's video, we're going to cover Newton's third law. So just to recap what we've been doing so far, we looked at Newton's first law, that an object in motion stays at motion and an object at rest stays at rest unless an external force is acting on it. We looked at Newton's second law. This was the big F equals ma vector equation that we've been using to analyze a lot of our situations. And we've also, in the last few videos, looked at some quantitative ways we can actually model forces like gravity, where we know the magnitude of the force of gravity is equal to m times g if we're on the surface of the Earth, and that's directed straight down towards the center of the Earth. And we know things like the force of kinetic friction is the coefficient of kinetic friction times the magnitude of the normal force. And that's always going to be in the direction opposite to the motion relative to the surface that's applying the friction. And we've hopefully start to become more and more skilled and able to use this sort of stuff to analyze a situation. We have a car on a hill or a block being pushed by something, and we've done some examples in our synchronous sessions, and hopefully we're getting used to that. Newton's third law sort of adds to all this. It doesn't change anything we have learned up to date, but it allows us to use those same sort of things and analyze more complicated situations. And what Newton's third law says is, it's been paraphrased a lot as, for every action, there's an equal and opposite reaction. Basically, can be thought of is if you push on something, that something is pushing back on you, and it has to do with this sort of object-agent relationship we have with forces. If you think back to when we first introduced forces, we said every force has to have two things involved with it. It has to have the object, the thing experiencing the force, and the agent, the object, the thing that's applying that force to the object. And Newton's third law relates to how we sort of relate the two and how we treat the forces in between that are occurring between them. So you can think of examples like this as we have, say, a hammer that's banging on a nail, right? That hammer clearly is exerting a force on the nail and driving it into the wood or whatever we're nailing. But if we were to, so in that case, we have the hammer would be the agent applying the force, and the nail would be the object we're analyzing, right? But we could also just look at the exact same situation and switch those roles, right? And in that case, if the hammer were the object that we were trying to analyze, then the nail would be the agent, and it would be applying a force on the hammer. And these two forces, right? This one here is the force the hammer is exerting on the nail, is going to be equal and opposite this force here, which is the force the nail is exerting on the hammer. So depending on which object we're analyzing, you can have this action-reaction pair where those forces are going to be equal and in the opposite direction. And that is true for every force that we will ever consider. So again, if we were to draw like this free body diagram type thing and include both forces, we can relate the force of object B acting on A is going to be equal to the force of A acting on B, just in opposite directions. All right, this may sound simple, well, just for starters, a lot of people can have a hard time accepting this, but I think some of the ways you can look at this hammer nail situation and realize that this is true is, imagine if the hammer was glass, right? That nail would shatter the hammer and break it apart. The other thing is, when the hammer strikes the nail, it accelerates the nail into the wood, but that hammer is also moving very fast. That nail slows down the hammer and accelerates it in the opposite direction. So you can see that this relationship is active. Both those forces are there. But there are some subtleties to this. What you would end up doing if you wanted to analyze these situations is we would analyze each object separately, right? We would look at a free body diagram for the nail, and we would have to include, the force from the hammer pushing it to the right. And then if we drew a free body diagram for the hammer, we would have that equal and opposite force from the nail that way. And we would know that this force and this force are equal in magnitude. And then that allows us to analyze both objects, gives us more equations that we've sort of created using Newton's laws to solve for whatever the things we don't know are. So it's going to look like this. You're going to have when we're analyzing multiple objects for a given situation. So let's say we have some person pushing a crate across the ground, and we want to look at both the person and the crate. We're going to have a free body diagram for each of them. And in each free body diagram, we're going to do the same sort of thing we've been doing to date, where we're going to identify all the forces acting on that person. We're going to circle them while they're touching the ground. So there's going to be some friction and a normal force. They're touching the block or the crate, so there's a force of crate acting on the person. And that's the only things touching that person. So we're on Earth. There's also the long range force of gravity on that person. We can do the same thing with the crate, where if we were to circle the crate, it's touching the ground, so it has a normal force on the crate and a frictional force from the surface of the ground on it. It's being pushed by the person, so it has a force of the push on the crate, or the force of the person on the crate. Nothing else touching it. Long range force of gravity. We have the force of gravity on the crate. So everything here in each individual free body diagram we've already done. It's the same sort of problem-solving strategy we've used in the past. The one big thing is Newton's third law allows us to relate the two. We see that these two forces form an action-reaction pair. In this case, the object that is experiencing the force is the person, and the agent is the crate. In this case, the agent is the person, and the object is the crate. These forces are going to be equal in magnitude. So we know F C on P, the magnitude of that is going to be equal to FP on C. And that's the gist of it. It sounds simple enough, but like most of these things, everything's simple until it's not. We're going to have to take a lot of practice and get used to using this, but it can really sort of extend what we're able to analyze so far to more complicated situations with multiple blocks connected by ropes and springs and whatever we want. So really quickly, let's start to get some practice doing this. So let's look at this situation. We have block B hanging from a rope across a pulley connected to block A on a frictionless table. The pulley and the string are both massless, which means the tension in this rope is constant. It's the same value everywhere in the rope. And this pulley just sort of redirects the direction of it. And in this case, with ropes and pulleys like this, the tension you can almost think of as just being a way of mediating the force between A and B. So the tension pulling on this is constant throughout the whole thing. So how would we analyze this? We want to draw free body diagrams, and the first thing we're going to do is draw a free body diagram for both of them. So if we start with A, first thing we do, we got to identify the forces. It is touching the surface of the frictionless table. So typically surfaces have friction and normal forces. This is frictionless, so we can ignore that friction. It's also touching the rope, so there is a tension on force A on block A. So we're going to call that one TA, and that's the only thing touching block A. There's also the long range force of gravity. So if I want to draw a free body diagram for block A, it's going to look something like this. I have that normal force I talked about. I have that tension force in the direction of the rope. We know tension's always in the direction of the rope or the wire or whatever's pulling on it. And I have the force of gravity acting on block A, pulling it down, right? I can do the same thing for block B, where I have block B over here. It's got, the only thing touching it is the tension there. That's, the tension on block B. And we've got the gravity on block B over there. So if I draw a free body diagram for that, I've got tension on block B pulling up, and I've got the force of gravity on block B, pulling it down. Sorry, I switched from G to F sub G here. Hopefully you can follow that. But I've drawn my two free body diagrams, and I haven't really used Newton's third law yet. There's nothing new here, but we've set up the same thing. Newton's third law comes in handy when I acknowledge the action-reaction pair here. This tension is from block B pulling block A. This tension here is from block A pulling back on block B. So I know that the magnitude of TA is going to be equal to the magnitude of TB. And I can just call that, might as well just replace it since they're the same thing with T. And I'll still have to keep in the signs plus or minus for whatever direction I use. But that's the gist of setting up these problems. One thing I always like to point out is with Newton's third law, action-reaction pairs, you will never see an action-reaction pair on a single free body diagram, right? Because remember, the action-reaction pair comes from the agent and object sort of relationship between those forces. And if you're drawing a free body diagram for one object or one agent, it's not going to have both forces in that pair. You shouldn't include the force acting on this object if you're drawing a free body diagram for this one, and vice versa. So Newton's third law is going to be applied to situations with multiple objects, and the pair, the Newton's third law pair, is going to relate forces on separate free body diagrams. So let's continue on with this. Let's actually add some numbers and we'll call it a day to this. But so to redraw this, we already have our free body diagram. I'm going to label them by their masses now. So same situation, but let's give it a capital M and a little m of 5 kilograms and 3 kilograms. So we have some numbers. Our free body diagrams, we just went through this. There's normal force on block M. There's the force of gravity on block capital M, and then there's that tension on block M. And for block lowercase m, we had this situation where we had the tension up and the force due to gravity on lowercase m pulling it down. So we've still got our free body diagrams. We're going to follow the same problem-solving technique we've been doing, right? 1, identify the forces. 2, well, here, let's write this out. 1, ID forces. 2, free body diagram. 3, coordinates. 4, Newton's second law, F equals ma. This is where we get our equations. You're going to have one equation for each dimension, each coordinate in your coordinate system. But now that we have Newton's third law and we're looking at multiple objects, this probably, when you get to this step, probably not enough to figure out everything you need to know. So we're going to repeat that whole process with the other object or another object. And, so then we'll identify the forces on a second object. And when we get to apply Newton's second law to that object, we'll get another set of equations that we'll be able to create for this situation. And slowly we'll have enough equations to solve for whatever the unknowns we're looking for. So let's do this. Let's start with block capital M. We're going to have to do both eventually. So we might as well pick that one. We've already done steps 1 and 2. Let's pick a coordinate system. Let's call this Y and this X. And so let's look at F net in the Y direction, and that's going to be equal to MAY, right? If we look at these forces, that means the normal force on capital M minus capital M times G is equal to mass times acceleration. There's no acceleration of this block in the up and down direction. It's staying on this surface here, so we know that acceleration is 0. We know the normal force on the block capital M is equal to M times G. So there's one equation we've got from Newton's second law. If we look at the Y components, we have F net in the Y direction, in the X direction is equal to mass times acceleration in the X direction. We only have one force here. We have tension, and that's going to be equal to mass times acceleration in the X direction. This is as much as we can do with this equation, right? We don't know the acceleration because you might be tempted to say it's zero, but we don't know that. It's going to accelerate this way. If you think about it, it's frictionless. We know there's some force pulling it to the right. We just don't know what that acceleration is, and we don't know the tension, so we're kind of stuck. So what do? We're going to go over here, and we're going to do the same thing for this block over here. We're going to pick a coordinate system. It's essentially a one-dimensional problem here. So we have F net y is equal to mass times acceleration y if we're looking in the y direction. If we look at all the forces, we have tension in the positive direction. We have negative lowercase mg, the gravity, in the downwards direction. And this is equal to mass times acceleration in y. And we're going to be careful here, and I'm going to throw in a little m here as a subscript to remind us that this is the acceleration of block lowercase m. This gives us another equation. So now we have three equations, 1, 2, and 3, for our system that we've created using Newton's second law. And we know that this t is equal to t. We did that on the last slide. From Newton's third law, we know that this is an action-reaction pair, so those magnitudes are going to be the same. The last thing we really need is there's an equation of constraint of motion here, right? These blocks are tied together, so if this one's accelerating down that way, this one is going to be accelerating that way at the same rate. That rope's going to stay tight, so they're going to move together with the same acceleration and magnitude. And what that means is what we've called AX here is going to be equal in magnitude to what I've called AY sub m there. But the trick is this is going to be a negative number. This is accelerating in what I've called the negative y direction. So I have to make sure I include that sign there. Right, so let's just call this A. A is equal to AX is equal to negative AY of little m here. Because, there's a positive acceleration for this block, there's a negative acceleration for this block, and they both have the same magnitude, so they're going to be doing that. This gives us our sort of final equation we need to connect all the ones we've made from Newton's second law applied to the multiple objects. And we're going to take this equation, call it star, and this equation, we'll call it circle, whatever, and we're going to just solve for t and a in that case. So I have t is equal to capital M times a. That's kind of sloppy. That's capital M. And over here, I have t is equal to negative ma, because I'm substituting this in for this. And I'm going to bring this to the mg to the other side, so that's plus mg. On this side, I have t is equal to m times g minus a, right? And since this t is equal to that t, right now we're at the point of it's just solving equations and it's algebra. So I know capital M times a is equal to mg minus a, lowercase mg minus a. I can do some more algebra on this and solve for my acceleration. I have m plus little m times a. That was pretty ugly. That's an a, sorry, is equal to g times lowercase m. All I've done is taken this term to the other side. So I know my acceleration is equal to m over m plus little m times g. And if I plug in the numbers, I know both the masses. I know 9.8 newtons per kilogram for lowercase g. This ends up being 3.68 meters per second squared is my acceleration. So we've solved for that. Now that I know the acceleration, I can just plug it back into either of these equations and sort out what my tension is. This one seems pretty straightforward. So if I plug in that capital M times 3.68 meters per second squared, and I plug in that 5 kilograms for my capital M, this ends up being 18.4 newtons is the tension. But again, so the last little bit is a lot of algebra on that we have to sort of get comfortable with. But the setup, again, why I really like the Knight textbook is because of these strategies. We're doing the exact same thing we've been doing this whole time. Identify forces, draw a free body diagram, pick a coordinate system. You apply Newton's second law in that coordinate system, and that gives us equations that we've created for this situation, right? This is one of the things I love about physics, and that is you will not be able to look up the answer to these problems in a textbook. You have to create those solutions yourself using these principles. But this, you get to Newton's second law, it gives you a set of equations, one for each coordinate system you apply them to, and then you can try to solve them. If it's not enough, we look at a different object. We look at block M or the other one, and then do the same thing, and we apply Newton's second law in another dimension. We get, with a different object, we get another equation we've created for this. Eventually, we get enough equations that allow us to solve for whatever we don't know. We'll work out more examples in our synchronous sessions. If you have questions, as always, email me and let me know, and we will sort it out.